Hello everyone. I still can't find the glasses, but we're just gonna have to power through because the MCAT doesn't stop for anybody. So let's go. Today we are talking about physics chapter 2, work and energy. Let's get started because this is a hefty chapter in terms of application. So again, these are just the concepts. I would definitely say pull up some practice problems, see how you're going to apply these formulas. But these are at least all of the ideas from this chapter that you should, mentally be able to say, okay, I understand how we would derive this formula. I don't understand this one. I need to watch something else. So this is just to, gather everything as a summary. All right, so let's get started. First, again, this is a lot of formulas, I'm sorry. First, we have kinetic energy, which is the energy associated with the movement of objects. So kinetic energy equals 1/2 mv squared, and the units for that is joules. Joules can also be written as kilograms times meter squared over second squared. So that is kinetic energy. Then we have potential energy, which is stored within a system. And the potential energy formula is, you can denote this as U, but it's mass times gravity times height. MGH is potential energy. Okay, so now we have elastic potential energy, and that is related to the spring constant and the degree of stretch of the spring. And so the elastic potential energy is written as U, again, potential energy, but that formula for a spring, or for an elastic potential energy specifically is 1/2 K, which is the spring constant, X squared, okay? Then we have power. Power is work over time. Power is the rate at which work is done. Power can also be found by this formula here, which is force times velocity, and the units for this is joules per second. It can also be watts. Also joules, newtons times meters, and then, as this part of the formula says, over seconds. Or again, a joule, like we said up here, is kilogram times meters cube, but then it's over seconds, which means you need this to be seconds cubed if you're using this for power. So this is just the varieties of the formulas. It's important to see how these formulas are derived. If you really write them out, you'd be able to see what cancels out and how you can manipulate these units. That's what I really did, and I better understand how to even know all of these formulas now, because I can see, what checks out and what you're actually doing with these formulas, instead of just memorizing, okay, this. Like, no, I know that power is, joules over second, and I know that this is a joule, so it makes sense, the joules per second, and I just have to make sure this is a cube because we're doing, the joules already has second squared. So just stuff like that, really understanding the concepts really helps with physics problems. And we'll see that later too when we get into the proportions of things. So where were we? Okay, so work is actually the dot product of force dot displacement, and that also means force times displacement times cos theta. And we know force is equal to mass times acceleration. So those are our first set of formulas, okay? So another part of the chapter was the work energy theorem, and that states that when net work is done on or by a system, the system's kinetic energy will change by the same amount of work that was done. So we're looking at the change in kinetic energy here, done or on a system. So, when work is done or is done by a system or is done on a system. So work itself is not energy, but it's the way that energy is transferred from one system to another. And we're going to get into that a little bit more, but also just up to this point, we have 3 different ways to calculate work. So one, we have force times displacement times cos theta. then here with this work energy theorem, we're seeing that work equals the kinetic final energy minus the kinetic initial energy, because as we said, the kinetic energy will change by the same amount of the net work that is done, if that makes sense. So just know that this is another formula for work. Oh, you can't even see it. It's down there at the bottom. It's work equals Kf minus Ki, which is kinetic energy final, kinetic energy initial. Okay? Because we're looking for this is going to be the change in kinetic energy, and the net work will change by the same amount as the kinetic energy. Okay? So that's how we get this formula. And then third, we have this down here. Work equals P delta V. So pressure times the change in volume. We look at that in another video, I believe. But that's just all the different ways that we've used work as of now. And just different ways that you can calculate it depending on what information you're given. Okay, so let's move on here to, excuse me, conservative forces and non-conservative forces. So we have conservative forces, which is when work is path independent, and it does when the work does not dissipate any mechanical energy. So what that means is, an example of that is like gravity or a spring. No matter the path taken by an object, when you're looking at a gravity or a spring, the same amount of work will be done, and that's a conservative force because the work done does not depend on the path taken. So that is when we can look at an equation up here that says, therefore, so based on this, and verbally based on this, we can get this equation to say that kinetic energy plus, the initial kinetic energy plus the potential kinetic, let me start over, I'm messing over my words here. The initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. Because when you are looking at conservative forces, there's nothing that's lost. So yes, the energy will change forms, but what you have at the beginning, you'll have at the end, whether that be in kinetic or potential energy. So that is important for conservative forces, is this equation, because you're not losing any energy when this occurs. But then we also have non-conservative forces, for example, friction. And friction is a non-conservative force because it does negative work on the mass. For example, if you're gliding something across the surface, right, and there's friction that occurs. That friction is actually creating thermal energy. That friction is working on the mass and producing thermal energy, which means you're losing some kind of energy in this process, right? So things like friction and air resistance, those things are non-conservative forces because the work that is done depends on the path taken. If you keep sliding back and forth, the work done is going to be, way more because the thermal energy is increasing by a lot. Whether if you just slide it once, that's different than sliding it back and forth to get there. So that's why friction depends on the path that is taken, which is why it's a non-conservative force. So the other thing about non-conservative forces is that they do not have potential energies associated with them. So when you're dropping something from, a certain height, that you can calculate the potential energy of that, because gravity, as we said, is a conservative force, and that gravity is always going to be a path independent. It's always going to be a path independent process in terms of the work that is being completed by the gravity, if that makes sense. And then we have, as we said, the non-conservative forces do not have a potential energy because they depend on the path taken. When I say they, I mean the work depends on the path taken. So when we have non-conservative forces, we have the the initial kinetic energy plus the initial potential energy plus the non-conservative work equals the kinetic energy, the final, plus potential energy, final. Okay, which means that the net work is equal to the change in kinetic energy plus the change in potential energy. Okay, so that's the difference between conservative and non-conservative forces. Now, a couple other things we didn't mention earlier. So chemical potential energy is energy stored in a bond. Then we have electrical potential energy, which is the energy between two charged particles. And finally, down here, we have our mechanical advantage and efficiency. Okay, so mechanical advantage is the force of the resistance over the force of the effort. And if it's an ideal machine, that can also equal the distance of the force over the distance of the resistance. So this makes more sense in a word problem context. You'll see what this means. But just as a general formula, that is, an important thing to remember. Okay, we're almost done here, but mechanical advantage as a concept is the factor by which a simple machine multiplies the input force to accomplish work. And that makes sense, right? Because it's mechanical advantage. It's, helping. It is making our, as humans, work easier to complete, right? And we use simple machines to do this. So inclined plane, wedge, wheel and axle, lever, pulley, and a screw are all types of simple machines that can give us a mechanical advantage. And mechanical advantage of an inclined plane is the length of the inclined plane divided by the height of the inclined plane. Okay, so that's for an inclined plane specifically. And one other thing we didn't mention earlier was that the total, you can still see it. The total mechanical energy is equal to the potential energy plus the kinetic energy. Okay. And now finally we have efficiency down here. I'm hoping you can see it. So efficiency is the work out over the work in, and that equals the load times the load distance and divided by the effort times the effort of distance. And again, something like that makes a little more sense in the concept, in the context of a word problem or something like that. So like I said, this is just to gather all of our thoughts and make sure we're like touching on all the things that we need to study and remember and learn. So if there's something in here that you don't understand, or you can't just say, okay, yeah, it's a refresher, definitely look into that in more detail, because the details are important. It would just take a very long time to go through a problem for each of these things. So this is just general formulas that you could take and practice applying to the problems. So if you have any questions, please put them below, and we will see you in the next video.